So, hi all, thank you for joining me today. Today I'll talk about cloud-wide contamination, chaining SSRF for tenant compromise in Azure, the CVE here. We'll start with brief introduction. First, a disclaimer. This research was conducted by me while working at Microsoft. Since then, I don't really work at Microsoft anymore. I work at Sierra. And this was conducted by me as part of Answer team, which is Azure Network Security Research Team. And my name is Vladimir Tokarev. I specialize in vulnerability research and Windows, Linux, IoT, OT, and Azure. Now, how does Answer usually conduct their research? First, we'll start by static analysis, going over the code, looking for bugs, issues. Then, if we'll have something promising, we'll start using a dynamic analysis tools. And it can be a burp, it can be actual something other as debugging. And then, let's say we found an issue, found a bug. In this case, we found SSRF, right? And so, from this point, we will create a report and set it to MSRC. After that, MSRC will forward this report to Azure Storage Resource Provider, because this is where we found the issue. And in some cases, those Azure Storage Resource Provider will create a report and publish it worldwide. In some cases, when the issue is critical. Now, how does usually a flow of SRP or Azure Storage Resource Provider works? It will start with Azure portal, from which a query will be sent to Azure Resource Manager, which is ARM. And then ARM will do some preliminary checks. After that, it will send the query to SRP, and SRP will actually handle it. Now, how this looks with aggregation. First, we have your subscription in Azure. Then you have under it the resource group that contains different accounts, for instance, the storage account. Now, storage accounts have a lot of different logics and functionality, such as file storages, queue storages, table storages, and blobs, and a lot more. Now let's jump to the end. This is the CVE, the vulnerability I have found, which is a server-side request forgery. And it's basically allow to perform spoofing over network. It allows a little bit more than that, and we'll dive into it. And it got a 9.8 critical score, basically because it broke some boundaries. Now, in Azure, there are basically 4 boundaries. There have a lot more, but those are the relevant to this example. First, they have the tenant trust boundary, meaning one tenant cannot touch another tenant's logic data or whatever. Another one is the control data pane, which means one data pane cannot access another data pane data flow. Service trust boundary, storage resource provider can't actually access and check and read network resource provider data, for instance. And the last one, network trust boundary, not everybody can access everything in Azure from the network, right? And so this vulnerability is pretty critical because it broke those boundaries. First, by bypassing the network trust boundary and bypassing the service trust boundary and hitting the control data pane, and then by actually bypassing the tenant trust boundary. And so this is what makes it critical. And now let's talk a little bit about the session roadmap, what we're going to do here today together. First, we'll talk about the SSRF discovery. Then we'll talk about Azure AD token leakage. Then we'll concentrate on DNS rebinding and spray and pray for bind attack. And then we'll talk about the full vector execution, impact mitigations. I'll hope we'll have some time for Q&A. So let's dig in. And so let's talk about SSRF. Now, SRP, Storage Resource Provider, is ARM Azure Resource Manager backend control pane for Azure Storage, which means ARM will do basic preliminary check on any request that is supposed to go to SRP, and then SRP will get it and proceed with the validation and checks. Now, storage resource provider had a lot of logic, as we said, and we can see here by the endpoints that are accessible, the aggregation we talked about. First, we have the subscription, then the resource group, and then the storage account, which are reducted for this demonstration. And then we have the actual logic there. We have the blob service, the management policies, file services, whatever. Now, one of those is the encryption scope. What is encryption scope? Basically, encryption scope is a concept that's used to encrypt different data of different users under one storage account. Right? We want to encrypt different users' data and then won't make it encrypted by same key. This is how we do it with encryption scope. And so let's talk about this process. How would it actually look like, right? Because if the encryption key is per user, so we'll need somehow to retrieve this metadata per user. And this is exactly how it will look like. We already seen part of this diagram, but first we'll have Azure portal sending some query to ARM. ARM will validate it basically and then send it again to SRP. After that, SRP, now you want to retrieve information per specific user, it will send a query to MIRP. What is MIRP? MIRP is Microsoft Identity Resource Provider. So it will send a query to MIRP and get back the answer, and then it can get the relevant information, such as encryption keys. Now let's take a deeper dive into how does exactly this whole thing works. Now we said that we have encryption scope, and basically one of the most popular functions in the encryption scope is the process encryption scope. It is used a lot because it's actually a method that's been called for different triggers, such as creating new encryption scope, updating it, removing it, etc. Now, this is a pseudocode of the method. There are a lot more logic there, and for security reasons, I didn't want to put it here. Now, basically, what we can see here is that we'll get encryption scope. We'll try to extract the identity URL or the delegated identity client secret URL. And after that, we will try, if it's not null, we'll try to use the get identity metadata async to retrieve information from this URL. If it's actually worked, we'll basically log it and save the encryption scope. Now, let's talk a little bit about what is the get this information from this URL. First, we'll have next logic. First, we'll send the get request to this URL. And then if the answer is 401 and the answer contains a specific header which called www authenticate, the authorization and the resource will be extracted from that header. Based on them, the code will generate AAD token, which is Azure AD token. And then it will send another request, which can be actually get or post to this same URL again. Then, for the second request, the answer will be serialized as identity metadata and will be stored. Now, basically what we have here. We have first get, then from this answer to this get, we will extract some data, and based on this data, we'll generate AAD token. And then we'll send a get or a post to this URL again with said AAD token. And then we'll parse the return answer and save it. And so basically, if attacker can manage the URL, they have a pretty sweet SSRF vulnerability here. And so a little bit about where we can trigger it from. There is another pseudocode, another method called refresh delegated resource identity async. Again, calling to this get identity metadata async. Then we have fetch identity metadata, and we have scrub encryption scope MSI credentials. All those pretty much triggering our interesting primitive, which is the get identity metadata async. And so now let's take a look at this primitive from the attacker's eyes. First, we'll need to create encryption scope, update it with the malicious URL, and basically it will trigger the SSRF, right? Well, obviously it's not that easy because this is protected by feature flags. What are those? Those are basically another security mechanism that put flags for a specific feature. For instance, if we want to use allow shared identities, to use shared identities, or those URLs we need to use, we need this flag to be on. And so we can read about this in the, obviously, Azure documentation. But basically, the idea is that is this flag is usually on, and so the answer is in corp accounts, which means in Microsoft accounts, workers accounts. This one can be turned with REST API, and in external accounts, it has to be with IT for a relevant region. Now, it basically means it goes some checks, and so. And like, if we look from the attacker's perspective, they probably could achieve that. For instance, they could maybe compromise corp account, or maybe they have an IT which works in Microsoft, their friend, and so potentially could be exploited pretty hard. So let's assume a breach for a sec. Let's say the flag is on. Now, what will the actual exploit look like? First, we'll need to create new encryption scope with a put request. Then we'll need to set the shared identity value. We'll need to set the default value such that every encryption scope will be used by default. Then we'll need to update the new encryption scope we created with this shared value. When we call the update will actually be the one that take the URL from the default shared identity and will put it in our new encryption scope. Now, this will trigger the SSRF. And so this is the example with webhook. We can see that was actually triggered. And if we'll check the IP, we can see that it was triggered from Microsoft Corporation, which means that we actually succeeded with triggering an SSRF from Azure, which is pretty cool. Nice. So now let's talk a little bit about what can we do with that, right? Because we remember that there was some AID token generation. Basically, it could be like, well, leak this to us because AID it's very strong, right? So again, let's take a look at that get identity metadata async. As I already said, first we have the get. Then if the answer is 401 and have www authenticate header, we will extract information from this www authenticate header. Based on that, create AID token and send get or post request to the endpoint. Again, the URL, the one that attacker manages. After that, the answer will be parsed and saved. How would it look between Azure Storage Resource Provider and MIRP? First, we'll have the get MIRP URL, right? The first get that we've already seen. Then MIRP will answer with the www auth header. Now, after that, based on this information, Azure Storage Provider will generate AID token and send it back. And then MIRP will get this token, validate this works, extract the relevant information, go search for this specific client metadata, and return it back to Azure Storage Resource Provider. And Azure Storage Resource Provider will send, OK. And so this is the primitive, right? Then get with ID token or post with ID token. And so the trick is, as long as the attacker can mimic MIRP's behavior, they will be good, right? So for the attacker to understand how they mimic this behavior, they first need to understand what is the www authenticate header and how it defined. And happily for us, Microsoft and Azure have pretty good definition of this in their documentation. So we have the authorization header and the resource header. And now let's talk a little bit about how attacker would exploit this together to get an AID token leak. For that, first they'll need their domain, right? Because they'll need to trigger a GET request to something they can intercept and get. So their domain will be a lot easier for this to do. And for instance, we have G1 and the 1L4 domain, which is Gandalf in lead. And so they have their own domain, Gandalf domain. Now, they also implement HTTP server, which basically logs every incoming request. And for GET request, will basically return 401 with www authenticate with the needed authorization and resource values in the header. And so back to the domain, we also need a DNS server. We'll need it later. We could potentially go with GoDaddy default values, like set there the HTTP server, but later we'll need the DNS server. And so here we'll also define a DNS server, which basically just the most trivial DNS answer for resolution for domain names, right? And so we set here the IP of the DNS server, which will then point to the attacker-controlled HTTP server. And so this is This is the POC, the first POC for the ID leakage. We can see the burp here triggering the request. On the right side, we have the DNS server. On the left side, we have the HTTP server. So we can see here to trigger GET request to the DNS. And then after some time, we will see the GET and the POST. And the POST contains the actual token as we wanted. So it was pretty cool. We successfully leaked the ID token. Again, pretty nice. Now, let's talk a little bit about how the full attack looked like, right? So first, we had the attacker creating a new encryption scope. Then they set the default shared identity. And then they updated the encryption scope, which basically meant merging the default identity URL into the encryption scope, which then again resolved in the SSRF being triggered. And then we had DNS resolved for the Gandalf domain. Then our DNS server returned the IP for our HTTP server. And then SRP sent the GET to our HTTP server, on which we returned 401 with www authenticate, with the bearer authorization and resource as needed. And then basically because we returned the domain with TTL0, there were another name resolution. And then the post GET was sent to us with the AID token. And now, let's talk a little bit about DNS turbining friends, or specifically, what can we do with the AID tokens in Azure? Basically, all of Azure uses Azure AID tokens. And so, for instance, we have the ARM that we already talked about, all control planes under ARM using AID tokens. Azure Storage, again, all of the actions on storage services require AID tokens. Blob, files, queues, all of those. Key vault operations, secrets, key, certificates, management, all of that will need AID tokens. Then we have Azure SQL and Cosmos DB. Those as well need AID tokens for database authentication. Then we also have the service-to-service communication, for instance, in the rare cases when network resource provider would like to communicate with computer source provider, they'll need AID tokens. And Graph API, user group app management, again, will need AID tokens for sure. And last but not least, Azure Monitor and Logs. It will need a lot of more things, but also AID tokens. And so, like everything in Azure uses AID tokens. What we can attack with that? Or we have this primitive that leaks AID token, and so what attacker can achieve with that? And so storage account vectors, basically SRP attacking SRP, right? So for instance, from here we could potentially trigger another request to another SRP endpoint and reset some stuff, modify encryption settings, access storage metrics, list storage accounts, stuff like that, which could be pretty cool. Then we could do cross-service operations. As I said, NRP attacking SRP, or in our case, storage resource provider attacking, for instance, network resource provider. Could be, again, very strong primitive. For instance, accessing Azure Monitor data or query Azure resource graph, stuff like that. It could be pretty powerful vector. Then we have Laravel movement. Maybe we can enumerate other resources in the tenant with this primitive. Maybe we can map out Azure infrastructure a lot more. Least but not least, the persistence vector, always good one. Maybe we can create backdoors. Maybe we can set up data exfiltration channels, modify access policies, plant malicious configurations. We could probably do a lot of stuff with that, right? And so again, is this that easy? Obviously not, because first we'll have this concept called scope. And so if we have scope mismatch, it won't work. And so in a lot of things that I described earlier, we'll have a scope mismatch because for instance, the ID is generated for SRP, and so maybe the ID that used in an NRP should be generated by NRP. And then again, it's different tokens, right? They're the same AID token, but they're not representing the valid AID token for a specific service. As I said, scope boundaries. Inner network isolation, again, make it very hard to jump between networks, which means, again, very hard to attack different services from this platform. Extra validations, a lot of specific validations per service, per request, per endpoint, very hard to bypass. Identity constraints, again, as we said, I have specific user identity. They can't access everything in Azure, so it's make it harder. Logic isolations as well, like we have different servers of Hyper-V running, and then, again, hard to bypass those. And like one of the important things that we actually didn't talk about, that we can't even send a request to the endpoint of our choosing right now, because right now we have this primitive that first get goes to us, and then the post or get with the ID token goes to us as well. And so as external attacker, we can't actually use this. We'll need somehow to make the SRP trick it to go to endpoints inside Azure, right? And this is where it's definitely doable. And basically, let's think about how could we do that. So current flow is Azure storage resource provider sends GET to Gandalf. Gandalf answers with 401, www-auth with the needed information. AD token generated, sent back with GET or post to Gandalf. Gandalf says the identity metadata. Now, what would be totally cool if we could implement DNS rebind technique? In our case, if we could first time return our IP, the actual IP of the HTTP server, and on the second time, for the same request, we could return an IP of something you want to attack in Azure. It could be totally cool, and this is how we'll do it. We'll do it with DNS rebind. In this context, like DNS rebind is big type of attacks relevant to DNS. In our case, DNS rebinding just means first time return our HTTP server, and second time return the target we want to attack. So how would we implement it in our DNS server? First, again, we'll log everything, and then we'll basically add this cool snippet, which is the whole DNS attack here. In case, like, if it's odd, return the target ID. If it's even, return our, like, the attacker HTTP server ID, IP. What will happen in this case? Basically, first time it will arrive to the attacker controlled HTTP, and second time it will arrive to the target IP the attacker wants to attack. And so this is the demo for that. On the right side, we can see the DNS server that first returns the same IP for the two first GET requests. And then we'll see third time, it will return another IP, which we're trying to attack here. And so here it is. Now, the interesting part here is we didn't see anything happens in the HTTP server, right? Even the first query haven't reached us. And so the question is why that happened. And basically the answer is, well, obviously they have DNS cache. Now, DNS cache, everybody knows what is it. DNS resolution is pretty costly, resources-wise. And so what we would like to do is to cache as many as possible DNS couplings with IPs and local cache, and update them every n time, right? And so this is the cache of DNS. Now, in our case, it means that our attack won't even work because the rebind technique first get the first query to the attacker controlled HTTP, second send it to the endpoint that we want to attack, but we have the first query will insert the domain in its IP into the cache, and then it means it will insert it for a few minutes. In our example, it was exactly 5 minutes, but then it means that the second query will arrive to us always. So this is how it will look like graph flows. First, we'll have the SSRF triggered. For instance, it even could be before that in the cache, and then all this attack means that the DNS cache active have the domain for 5 minutes. Well, basically, won't be the second attack to the targeted endpoint. It's pretty sad. And so next step will be for the attacker, how would they bypass it, right? Now, the solution, something that we calling spray and pray for bind. Basically, what would be the idea? The idea would be, let's trigger a lot of SSRFs in a 15 seconds interval, And because the cache will hold the domain with the IP coupling for 5 minutes, with 15 seconds interval, will sometime near the 5 minutes, we'll probably hit a sweet spot where the first query will be to our control domain, to the good domain, the attacker domain, the HTTP server, and the second one will be triggered when the cache refreshed, and then this will be actually triggered again, and our DNS server will return the target IP we want to attack. So this is exactly what I described here. Trigger SSRF every 15 seconds. Each SSRF creates 5 minutes cache window, and then eventually one attempt, mainly the attempt that closest to the 5 minutes mark, will win this race, let's call it. And how the winning will look like. First, the attacker will get the IP cached. Then it will trigger every 15 seconds, and again, the one that most close to 5 minutes will refresh it. And so this will win, and we'll have second query sent to the target IP we want to actively query. And so this is how it look like, again, on like time scale with flow. We'll have a lot of SSRF triggered, and then near the 5 minutes mark, we'll have one that actually wins second time, and this is exactly what we are after. Now, let's look at a demo of that. On the right side, again, we have the DNS server. On the left side, we have the HTTP server. Now, we're actually interested in looking at a place where we only see the GET and not the POST, because it means that the GET was actually received by attacker-controlled HTTP server, and the POST were actually sent to the target endpoint, which will actually mean that the spray and pray for bind attack actually worked. And here we can see a lot of GET and then POST attempts. Actually, this POC took more or less 5 minutes, and I just cut it short because we don't want to look at it for 5 minutes. And in the end, we'll see actually only the GET query, which is exactly right now. And this means that the POST was sent to the target IP, which again, basically means that the spray and pray for bind worked. And now, this was the flow. Now, actually, it's not exactly the flow because a lot of SSRF attempts are missing from here. But basically, what we get is first SRP tries to resolve Gandalf, then DNS attacker server will answer with the pointer to the HTTP server. Then the GET to the HTTP server will be sent, and the answer with 401 and www authenticate, bearer authorization, and resource will be sent back to SRP. Then SRP will basically do a lot of resolve because of the SSRF, but the winning attempt will actually resolve again Gandalf, and this time our DNS, like the attacker DNS server, will actually return an IP. The SRP will send the POST or GET with the ID token too, which is pretty cool because now we control what we try to attack, right? Now we actually can make SRP attack something for us, which is pretty dope for the attacker perspective. For the defender perspective, it's not that dope for sure. And now, after we can do this kind of request, what should we do, right? We had a lot of primitives or a lot of vectors, attack surface we could potentially exploit this into. First, we have the Azure Storage Resource Provider attacking Azure Storage Resource Provider, as we said, like changing information for encryption scopes for other users, maybe deleting some files for other users, stuff like that. Then we had, for instance, Azure Storage Resource Provider will attack compute resource provider, another cool vector we could take, lateral movement, and persistency. Now, the truth is that I searched for surface and vector attacks on all the four, and actually the only promising one that I succeeded to exploit were Azure Storage Resource Provider, attacking Azure Storage Resource Provider, again because there are a lot of different mitigations, scope mismatch, stuff like that. There are a lot of mitigation, and so the actual vector that I could manage to do was SRP attacking SRP. And so let's talk about how we started. Basically, we had those endpoints that are the logic that SRP can do for us, for the user. Another cool SRP endpoint is regenerate password. What is a regenerate password? Okay, so basically, user can have SFTPs or blob accounts or any manageable idea that hold files, right, for different users. And this obviously will have SSH password. Regenerate SSH password, basically what it does, it gets all those parameters and creates a new password for that specific SFTP account, folder, whatever. Now, this is the another assumed breach scenario we'll need to take into account, because if attacker want to execute this attack on other tenants, they need to know all this information. First, they'll need to know the account name, the resource group name, the subscription ID, and the username. Now, on one hand, this is like pretty private information, and it's pretty hard to get. On the other, those aren't secrets or passwords, so they usually stored a little bit less securely, right? So I bet I can like go on different GitHub repos and find some of this information for users, for example, already seen this, right? And so potentially attacker could get this. It won't be that easy, but this is why we have another assumed breach. This is it. Attacker can get this information for the relevant account they want to attack. Now, let's say they got this information and they send this request. They have or 200 return OK code or other codes indicating error. Now, if the 200 OK was returned, they also will have a plain JSON with SSH password string, which is pretty dope, right? And so in this case, they can potentially execute this for other tenant, right? What we're trying to do here is first trigger the get, then use the spray and pray for bind attack, then with that attack, manage SRP attacking another SRP instance for different tenant. And this is the attack vector. And this is what we'll see here. And so, yeah, on the right side, we have the GIF of Gandalf shaking his head. I love Loader very much because this is why we have it. On the on the left side, we have SFTP, a victim user uploading this GIF into the SFTP. Now, the attacker attacks this SFTP account with the spray and pray for bind attack we talked about. Again, right side DNS, left side HTTP. Again, on the left side, we're waiting to see only get receiving, because that would mean that the other requests were sent to the SFTP store account and regenerate the password. And this is what we see in the end. This is exactly that. And now the victim will try again to connect to the SFTP account, and they will fail because, well, the password was regenerated, and now they can't upload memes to SFTP of Azure, which is really sad reality. So yeah, they have been attacked. And so this is the attack flow vector that we've seen here. First, create an encryption scope, then set the default shared identity, then trigger a merge, which will basically trigger the SSRF. Again, here I don't present the SSRF at times because it will make this diagram a lot longer. So after the SSRF triggered, we'll have first resolve for Gandalf domain, then the first get will be sent to the attacker-controlled HTTP server. The attacker will answer with 401 and www authenticate with the needed information. Then after the winning attempt of the spray and pray for bind attack, another result for Gandalf domain. And again, now the IP is different. Now the IP pointing to another SRP instance, and then we'll send the regenerate password to this SRP, and actually with the liquid information, and we'll actually change the password for this SFTP instance. Now the answer will contain the actual SSH password. Now currently, what this primitive gives us, basically a persistent dose, because now we can basically trigger it a lot of times, and well, specific users that we can leak their information couldn't use their SFTP accounts, for instance, right? Now, the question is, can we do more, or can this be exploited into something stronger? And so we've seen that the answer actually contains the SSH password. Now, let's talk about the scenario that attacker can get this SSH password. Well, basically, it means real game over, because now they can upload malicious binaries into these files, maybe even patch some files, steal credentials from there, do whatever they want, which is real game over by win state for the attacker and lose for the defender. And so let's take a look at how this metadata, or in this case, the SSH password, is being handled. Basically, we can see that this information being logged. And this is the pseudocode, again, for the log identity metadata. It's not all the code, but it's not a lot bigger than that. And basically, the idea is that the identity metadata will be deserialized into, the answer will be serialized into identity metadata struct, which is permissive. This means that new fields that don't exist in the original identity metadata will be stored as well. I guess it's like a future-proof thing. And then we will go on this metadata structure and redact all the relevant reduction list values, such as client secret, password, token, key, stuff like that. Now, SSH password wasn't one of them, and so this means that the SSH password that we get back won't be redacted, and so it will be logged, which is, here we can see the serialized metadata, which will literally be stored in the log as plain text, which is pretty cool, right? And now what we understand from that first, potentially if attacker can get it, they'll win, totally win, like storage account takeover. And so how would they get it? First, they can access log systems potentially, which will be a little bit hard because in Microsoft to do that, to access the systems that can view logs, you'll need to use specific external hardware called YubiKey, and so it's pretty hard. And on the other side, they'll need to sniff on the network for do that because again, the answer sent plain text. And so if they can sniff it, they can use it. Again, this is pretty hard because sniffing on the network between two SRP instances it's pretty hard task. They probably need to execute code on this network somehow. Again, pretty hard to do. And overall, I won't say it's not possible, but it's very hard to do. And this is lead us to the next stage of we have a pretty strong primitive here, right? We can actually trigger SSRF that will leak us the ID token, and furthermore, we can attack another instances of SRP or other services with this ID token, with this SRP instance. And so how come this is, well, we can't totally dominate the world, right? How come we didn't finish with total win of all Azure? In worst case scenario, we showed that we can have storage account takeover, not whole Azure. And so the answer is that basically Azure have tons of security implemented in a lot of layers. I won't go all of them because it will take me another hour for easily more than that. But they have a lot of basic things that make attacking this a lot harder than it can be. First, they have network isolation and segmentation. Again, different networks, we can access those. Everything is SDN and SDNs, which are software-defined networks, a lot of validation, a lot of firewall rules on those, hard to bypass. Then again, almost everything everything that is external to Azure and internal is HTTPS and TLS. Again, very hard to bypass that. Telemetry and log access controls, as we said, we have specific hardware we need to use for that. Again, hard to steal it. Then computer isolation and host security. We have specific flavor of Hyper-V for Azure servers, and there are a lot of more of those. Those are making life harder. So the mitigations for this attack were implemented by SRP were mirror-based URL validation with regexes, DNS rebinding mitigations, cache different TTLs. If now we have random TTLs, the attacker won't know if the attack worked or it's the cache. More reduction of important data. Now we redact the SSH password, obviously. Internal monitoring enhance. They were also there before, but now they have this on SRP. And the key takeaway here is that don't trust external inputs in identity resolution. All the attack was possible because of that. Secret logs are secretly exposed. If you keep SSH password in logs, somebody will use it to attack you sometime. And all kicks, new tricks. All this presentation, all this vulnerability is based on old concepts, nothing new here. They just work. Special thanks to MSLC and to SRP team, and we have now Q&A time. Thank you.
りがとうございました。それではご質問を一つお受けしたいと思います。We have Q&A time. If you have a question, please raise your hand. Our staff will bring a mic to you. We will take one question.
Yep.
どなたか、はい。もう一度手を挙げていただけますか？ Could you raise your hand again?
As a user of the Microsoft, then how can a user detect such attack happen?
So the cool part, oh shit, don't want to hear me. The cool part is that after we reported that and they implemented all of this, they actually scan for this type of behavior on the network. So they're actually doing this work for you. But then again, how would you bypass that? Always try to use MFAs, like multi-factor authentication methods for different things. I know that SFTP actually have those. And so if you enable this, even if I can link this as a password, it won't be that easy to actually blocking you from using it. So this is my answer on that. Thank you.